Every forensic investigation begins with data, gigabytes of it. But manually sifting through disparate logs and reports is not just time-consuming, it is exhausting. And in that exhaustion, crucial connections are missed, vital evidence remains hidden, and the full story of an incident is lost. That is the cost of manual correlation. What if you could automate that insight? What if the potential hidden within your data could be unlocked instantly? This is CrowEye. Every digital forensic investigation begins the same way. We collect artifacts, we run tools to parse the master file table, the registry, and the event logs. But once you have 10 different CSV files on your desktop, you are left with a manual nightmare. You are the one who has to remember that a timestamp in the prefetch correlates to a file creation in the USN journal. Manual process of copy-pasting notes into your forensic notebook just to keep track of these crucial connections. The CrowEye correlation engine was built to automate that mental heavy lifting. It does not just display data, it builds relationships. I am going to walk you through the entire graphical user interface, from importing outputs from your favorite external tools to uncovering the forensic narrative hidden in the noise. By the end of this video, you will know how to turn raw bytes into a timeline. Looking at the main interface, we have three primary tabs that define our workflow: the Pipeline Manager, the Execution tab, and the Result Viewer. We start here in the Pipeline Manager. In the upper section of this screen, you will find your pipeline metadata. This includes the case identifier, pipeline name, description, case name, case ID, and the name of the investigator. When you run the correlation engine for the first time, it will automatically create a pipeline using default metadata. This is based on the case identifier you set during the initial CrowEye run. By default, it will be named Case Identifier Default Pipeline, but you have full control to change this or add more granular details to suit your specific investigation. In the bottom half of the Pipeline Manager, the screen is split into two sections, one for feathers and one for wings. In each of these sections, you will find three essential buttons: Add, Create, and Remove. The feathers let us start at the beginning, the feather creator. In the CrowEye ecosystem, we refer to normalized high-performance data as feathers. While CrowEye has its own collectors, the engine is designed to be tool agnostic. If you are a fan of the tools created by Eric Zimmerman, like PECMD, Amcache Parser, or EVTXCMD, you can bring that data directly into the engine. When you open the feather creator, you will see an interface designed for mapping. You point the tool to your CSV or JSON output, and then the magic happens. Furthermore, if you have already parsed data using the internal parsers of CrowEye, the engine will automatically convert those outputs into feathers the first time you run it, saving you the manual import step entirely. Now, let us walk through the process of creating a new feather from scratch. When you click the Create button in the feather section, a dedicated configuration window appears. At the top, you will define your feather name and the save location. By default, CrowEye intelligently directs these to your case-specific folders, either correlation config or correlation feathers depending on the version you are using, ensuring your forensic workspace stays organized. To demonstrate how this works, I am going to import a SQLite database previously generated by a CrowEye parser. We start by clicking Browse Database to select the file we want to convert. Once the file is loaded, you will notice that the engine automatically detects the artifact type based on the metadata and naming convention of the file. While this auto-detection is highly accurate, you always have the option to override it and select the type manually. Additionally, if you are working with a multi-table database, you can use the drop-down menu to select the specific table you wish to ingest. The heart of this window consists of two interactive grids. The first is the column mapping table. This gives you granular control over your data architecture. You can select only the specific columns that are relevant to your investigation, or unselect the noise to keep your feather lightweight. Even better, you can rename columns on the fly. If you want to change a source column name to better align with your overall timeline, simply type the new name in the mapping field, and it will be updated in the generated feather. While the process is virtually identical for other formats, there are slight variations for CSV files. For instance, when importing a CSV, you will see a delimiter section where you can select or define the separator, whether it is a comma, tab, or semicolon, ensuring the engine parses the structure correctly. Before you finalize the build, take a look at the Data Preview tab. This allows you to inspect the raw input data one last time to ensure every column and value is exactly where it should be. Once you have verified the setup, clicking Import to Feather will transform that raw file into a high-performance query optimized feather ready for the next phase of your analysis. Let us move to the Wing Creator. This is where the forensic logic is defined. In this interface, you will see three primary tabs: Basic Configuration, Scoring, and Semantic Mapping. We shall start our focus on the basic configuration, where you define the core DNA of your forensic rule. The first section is Wing Information. This is where you provide the essential administrative details. The wing name, a unique wing ID, a clear description of the purpose of the rule, and the author name. Proper documentation here is key, ensuring that as your library of forensic rules grows, every wing remains searchable and its purpose is clearly understood by other investigators. Next, we have the correlation settings. This section defines the scope of your analysis. You can configure the wing to target all applications for a broad environmental sweep, or you can focus on a specific application. If you choose a targeted approach, you can provide the specific application name and even the application path. This is a powerful way to eliminate background noise and focus the resources of the engine on a known suspicious process. Just below that is the time window setting. This is a pivotal value for the engine. In the time window scanning engine, it defines the temporal boundaries for your scan. This value is also used to collect and organize evidence into anchors. It effectively tells the engine how close two events must be in time to be considered part of the same activity cluster. Following this is the anchor priority. This setting allows you to tell the engine which artifact should be treated as the source of truth. By assigning priority to a specific artifact, like the MFT or AMCache, you ensure it serves as the primary anchor for the resulting identity timeline. The final section of this tab is the wing logic here. You should explicitly state the forensic goal, what this wing is trying to prove, such as evidence of execution or data exfiltration. Crucially, you will set the minimum matches required. This acts as a high-pass filter for your results. If you set this to 3, the engine will only create an identity if it finds correlating data from at least 3 different feathers. Any matches that fall below this number will be ignored, ensuring that only the strongest multi-source evidence makes it to your final report. Now, let us navigate to the next tab, scoring. When you enable weighted scoring here, you activate the sophisticated confidence scoring for this specific wing. This is a powerful feature if there's any conflict between the scoring weights of the wing and the global system-wide scoring weights. The scoring weights of the wing will always take precedence. This allows you to fine-tune the relevance of evidence specifically for the hypothesis. This wing is designed to test. After you link the necessary feathers to this wing, you will see them listed in the featherweight table. Here, you can individually adjust the weight assigned to each feather, allowing you to prioritize artifacts that you consider more forensically sound or relevant to your current investigation. Below this, you will find the score interpretation thresholds, which allow you to adjust the boundaries for what constitutes high confidence, medium confidence, or low confidence results, tailoring the reporting to your specific needs. Moving on to the semantic mapping tab. This tab is your gateway to enriching raw forensic data with contextual meaning. Here, you will find a table pre-populated with default semantic rules loaded from your global settings. There is a convenient button to load global semantic mappings, ensuring that if you have updated your overarching rules, they can be immediately applied to the swing. Of course, you have full control to edit, delete, or create entirely new semantic rules tailored to the specific investigation. Let us explore how to create a new semantic rule, as this is where you infuse true forensic intelligence into your analysis. We offer 2 primary modes, simple and advanced. The simple mode is designed for direct, one-to-one mapping. You use this when you want to link a specific input value, such as a log number, to a predefined semantic output. You shall set the source of the semantic input, the feather, the field name within that feather, and the exact value you are looking for. Then you define the semantic data you want to associate with it. For example, mapping event ID 4624 to successful login. Finally, a description field allows you to document the purpose of the rule, aiding future investigations and team collaboration. This mode is straightforward. If the specific value is found in the specified field, the semantic tag is applied. The advanced mode offers a much more powerful and flexible approach. First, you create a descriptive rule name and define the core semantic value it will apply. You then categorize it and assign a severity level, for example, critical or warning, along with a comprehensive description. The key difference lies in the input conditions. Unlike the simple rule, which looks for a single value, the advanced rule allows you to construct complex logical expressions using and/or logic. You can add conditions from different feathers and different fields. Building a nuanced set of criteria, for instance, you could say if process name from an AMCache feather and destination IP from a network log feather both match certain values, then tag this activity as lateral movement attempt. The engine will only apply the semantic mapping if all specified end conditions are met, or if any of the OR conditions are met, providing robust context to your correlated results. As you build these complex rules, a logic preview section helps you visualize and validate your conditional statements. The execution now, with our feathers prepared and our wings meticulously crafted. it is time to move to the Execution tab, the control center where the correlation magic happens. At the top of this tab, you will find the Pipeline Overview section, which provides a summary of the current pipeline, including its metadata and selected configurations. Below this is the wing selection area. Here, you will see a list of all available wings, the powerful default wings provided by CrowEye, alongside any custom wings you have created. By default, both primary default wings will be selected for comprehensive analysis. However, for faster execution and more focused results, I highly recommend selecting only the specific wing or wings most relevant to your current investigative hypothesis. This optimizes the engine processing time by directing the resources to only the rules you need. This section is also where you select your correlation engine. You have a choice between the identity engine and the time engine. The identity engine excels at tracking specific entities, like a file or a process across your dataset, building a story around its lifecycle. The time engine, on the other hand, is designed for broad temporal scanning, ideal for uncovering general activity patterns and relationships within defined time windows. I will be demonstrating the results from both engines to illustrate their unique strength. Further down, you will find the output location for your results. By default, CrowEye pre-configures a logical path within your case folder, ensuring all your correlation outputs are neatly organized. For this demonstration, I will keep the default setting. Crucially, the time filter section is located here. This feature is invaluable for efficiency. By setting precise start and end times, you instruct the engine to focus its analysis only on the relevant temporal window. This dramatically reduces the dataset size for processing, allowing the engine to skip vast amounts of irrelevant data, significantly accelerating your investigation and enhancing the clarity of your results. This ensures that you are not waiting for the engine to analyze data from last year, if your incident happened last week. Before we initiate the correlation, I want to highlight a crucial point regarding the overall performance, especially concerning semantic mapping. While semantic mapping is incredibly powerful for enriching your results, applying it can significantly increase processing time, as it involves extensive lookups and rule evaluations. If you are prioritizing speed for an initial triage, or if the resources of your machine are constrained, I highly recommend going to the global settings of CrowEye and temporarily turning off wing semantic mapping. This can drastically cut down execution time when you do not immediately need the in-depth contextual tagging. Now, let us return to the Execution tab. With our configuration set and our chosen engine ready, all that is left is to press run. For a regular system, analyzing all artifacts for a typical computer can take anywhere from 3 to 10 minutes without semantic mapping, and 10 to 30 minutes with semantic mapping enabled. These times, of course, are highly dependent on the power of the machine running CrowEye and the volume of data. To skip the waiting time, which we do not have in this demonstration, I have already pre-correlated some results. To load previously generated results from this case, we simply press Load Last Results. This opens a dialog where you can browse and select any prior correlation run. For our demonstration, I have prepared 2 distinct results to showcase the power of both engines. One result from the identity engine, using a proof of execution wing that integrated data from 14 different feathers, with semantic mapping turned on. This will show us how the engine traces specific execution events with rich context. 2. Another result from the time engine, utilizing a user activity wing from 7 feathers, and with semantic mapping turned off. This will highlight its efficiency in identifying broad temporal patterns without the additional semantic layer. Let us load these and move to the result viewer to see what they reveal. Let us begin our exploration in the Summary tab. This initial view provides a high-level overview of your correlation run. On the Stats panel, you will find key metrics, the execution ID, the total number of wings used, the overall number of matches discovered, and the time used for the entire correlation process. Below these statistics, we have 3 insightful charts. The first 2 visualize the number of matches by feather. One presents this data in a detailed table, and the other in a clear pie chart giving you a quick visual breakdown of where your correlations are originating. The final chart illustrates the data extracted from each feather. You might notice that some feathers have a significantly lower extraction rate compared to others. This often depends on your initial correlation settings, particularly if you have set an older time filter. Artifacts that update frequently tend to overwrite older data, leading to fewer extracted historical records. Conversely, you will typically find a high volume of data from the master file table and the USN journal, as these artifacts are designed for comprehensive logging and do not frequently overwrite or delete their historical entries. This valuable summary data is available for every correlation run you perform. Next, let us dive into the Identity Result Viewer. As you can see in this tree view, we have 6 main columns: Identity, Anchor, Evidence, feather, score, and semantic. Additionally, 2 helper columns, evidence count and anchor count, provide quick quantitative insights. You will notice many identity names, some appearing as different variants. Each variant represents a distinct path or form of that identity and will have its own set of extracted feather data. When you click on a sub-identity, it expands to show its associated anchors. Clicking on an anchor will then reveal the actual evidence records that constitute that specific event. For a detailed view of any identity, you can click on its dedicated identity icon, which opens a dialog box with comprehensive information. For a broader overview of all the information gathered from various feathers pertaining to that main identity, simply click on the main identity icon. As you hover over the semantic data in the results, a tooltip will appear, displaying all other semantic tags and interpretations associated with that specific match, providing immediate context on the toolbar. You will find a search bar where you can quickly locate specific data or identities. We are continuously working to enhance this feature to include searching by semantic value in future updates. Next to the search bar is the feather menu, allowing you to filter results based on specific feathers you wish to examine. The adjacent drop-down menu allows you to set a filter for the minimum evidence count, displaying only identities that meet a certain threshold of supporting artifacts. The pagination controls on the far right enable you to efficiently navigate through large sets of evidence. Now, let us switch over to the time-based result viewer. In this view, you will observe the data organized under different time windows. The default time window here is typically 3 hours. Next to this, you will see the number of identities and the records or evidence associated with that window. Below this, the structure mirrors the identity result viewer. Identity anchor evidence. The search functionality is similar to the identity viewer, but with one key difference: a dedicated time range filter. This allows you to narrow down your analysis to a precise chronological period, further refining your results. And with that, we have completed our tour of the CrowEye correlation engine. While I have kept this video concise, I want to mention that during the correlation process for this demonstration, I use my main machine, relying on the default parsers and wings to generate these insights. Thank you for joining me. See you in the timeline.